Hi guys, today we're starting a new topic. This is actually matric work. We are doing mathematical induction. Now, mathematical induction is not a big section really. It's basically just a way of proving a mathematical statement. We're going to have to use specific steps. In a question like this, they will state that you need to prove by mathematical induction, and then you know that you're going to have to follow the specific steps. So I have listed all the steps here, as you can see, steps 1 through 5, and all we're going to do is we're going to do some examples. Yeah, we'll see how it goes. We might do 2, 3, even 4 examples, and then you're just going to practice a few of these for homework. Now, there are two types of questions that they can give you for mathematical induction. So today we'll only do the first type, and then tomorrow's lesson will be on the second type. But before we go to the example, let's just quickly run through these steps. Now, it might seem a bit confusing because you haven't seen an example yet. But yeah, let's just run through them, and then obviously we'll practice the steps when we do the examples. Okay, so the question will state what you need to prove, but then your first step would have to write down what must be proved as RTP. So RTP, just grab my pen here. RTP, I think we have used this before, but this just stands for required to prove. Required to prove. So you will write RTP and then a colon, and then you'll actually write the statement that they're asking you to prove. You will write it down mathematically in terms of n. Okay, you can actually use any letter, but we'll be using n all the time. So yeah, it makes sense to keep using that one. Then what you're going to do is once you've written that statement down, you're going to prove that the statement is true for n equals 1. Okay, and for these questions also, you'll see that in the question they'll always state that you need to prove that the statement is true for n, an element of natural numbers. Now, hopefully you can remember that natural numbers are all the numbers from 1 and up, all the whole numbers from 1 and up. So that's 1, 2, 3, 4, 5, and so on. So we're not going to worry about 0. We're not going to worry about negative numbers. We're also not going to worry about fractions or decimal values. So we are only going to be working with natural numbers. So we're going to prove that the statement is true for the first natural number, which is 1. Okay, then our next step is going to be to assume that the statement is true for n equals k. So we're then going to introduce another variable. We're going to say assume that the statement is true for n equals k, and then we're going to rewrite our original statement that we wrote in terms of n. We're going to rewrite it using k instead of n. Okay, and we're going to say that we assume that that is true. Then we're going to use that assumption in our next step to prove that it will actually also be true if n is equal to k plus 1. And this, step 4, is usually the kind of labor-intensive step. We're going to have to do some algebraic manipulation. You'll see when we do the examples. But we are going to prove that if the statement is true for n equals k, which will represent any natural number, then it will also be true for n equals k plus 1. So what does that mean? That means that if the statement is true for n equals 4, then it has to be true for n equals 5. But if it's true for n equals 5, then it has to be true for n equals 6. If it's true for n equals 6, then it has to be true for n equals 7, and so on. And since we proved in step 2 that the statement is true for n equals 1, and then in step 4, we're basically proving that the statement is true for consecutive numbers, consecutive natural numbers. If it's true for n equals 1, then it has to be true for n equals 2. If it's true for n equals 2, then it has to be true for n equals 3, and so on. So if that is true, then the statement will be true for all natural numbers. Okay, so that is basically the premise. That is how the method of proving works, mathematical induction. Okay, so the first example here is we are going to look at summations. Prove by mathematical induction that the sum of the first n natural numbers is n times n plus 1 over 2. All right, so now again you can see, or not again, but immediately you can see that we're talking about natural numbers. Okay, we need to prove using this method that the sum of the first n natural numbers is n times n plus 1 over 2. Okay, so our first step, and I'm actually going to list these as steps. You don't have to when you're doing the actual proof, but step 1, we're going to say required to prove. And now instead of writing the words, the sum of the first n natural numbers is this, we're going to write it down mathematically. So the first n natural numbers, we're going to go 1 plus 2 plus 3 plus dot 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 plus n is going to be n times n plus 1 over 2. Right, like that. That is basically what we are needing to prove. They're saying the sum of the first n natural numbers, so it's going from 1 all the way to n, is going to be that. Okay, step 1 done. Step 2. Now we're going to prove that the statement is true for n equals 1. Right, so now we're going to say for n equals 1. What is the left-hand side of this statement? If n is equal to 1, then how many terms do we have here? If n is equal to 1, we only have one term. We only have that first value, right? Because they're saying of the first n natural numbers. So if n is 1, that's just of the first one natural number, the first natural number. So the left-hand side is just going to be 1. Okay? Now let's look at the right-hand side. The right-hand side is going to be, n is now 1. So it's going to be 1 times 1 plus 1 over 2. Which if we simplify that, it's 1 times 2, which is 2, divided by 2, which is 1. So we see here that for where n is equal to 1, the left-hand side is equal to the right-hand side. So therefore, left-hand side equals right-hand side. Therefore, true for n equals 1. Okay, there we go. Step 2 is done. Now, step 3, let's move this up, is where we are going to assume that the statement is true for n equals k. So now we're going to say assume true for n equals k. And now we're actually just going to write down what that means. Oh, let's also just add, let's just add that k now, this new variable that we are introducing, also just represents all natural numbers. Okay, please just remember to add that whenever you're introducing a new variable, you need to state that it is natural numbers or that it represents natural numbers. Okay, so now we're basically going to rewrite this whole statement and we're just going to use k instead of n. Okay, as easy as that. So we're going to say 1 plus 2 plus 3 plus, and then just dot 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 to show all the numbers in between, and then plus k is going to be equal to k times k plus 1 over 2. All right, so now this is an assumption, guys. We are assuming that this is true. So what we're going to do now is that we are actually going to use this in step 4, right? Because let's just go back up to the list of steps. We're saying prove that if the statement is true for n equals k. So if this is true, if this side, 1 plus 2 plus 3 plus k, is equal to k times k plus 1 over 2, then this same statement will be true for where n is k plus 1. Right, so that's what we're going to prove. So look at what I'm going to do. For step 4, now I'm going to just write down for n equal to k plus 1. Right? The left-hand side. So now we're looking back at our original statement, and instead of n, we're going to use k plus 1. Okay, that's what we're doing. We're going to say 1 plus 2 plus 3 plus dot 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 plus k plus 1. So that is the left-hand side, all right? Because that now, n is now k plus 1. And what do we need to prove? We need to prove that this is going to be equal to Let me write it in pink. Hope you can read this pink. It's a bit light. Let me use a different one rather. Have a different pink one that's a bit darker. So if we do that, so we are going to try and prove right? That is the same. If we're making n equal to k plus 1, then we have n times, so k plus 1 times n plus 1. So k plus 1 over 2. Now if we just simplify that, we have k plus 1, k plus 2 over 2. That's what we need to try and prove. We need to try and prove that this statement can actually be equal to that. Because if we're proving that, then we are proving that this statement is true if n is equal to k plus 1. All right? And we've made this assumption. Now what I want you to think about is, if our last term here is k plus 1, right? Because that is what this means. If we're saying that this first n, what's it called? The first n natural numbers is 1 plus 2 plus 3 plus ... and then the last term is k plus 1. What is the second to last term? The second to last term is actually equal to k. So I'm going to rewrite it like this. 1 plus 2 plus 3 plus ... plus k plus 1. Right? I hope that makes sense. If the last term is k plus 1, then the second to last term is k. Now, what do we have here? We have that 1 plus 2 plus 3 plus ... plus k. We have it there. And we assume that this statement is true. So we are assuming that this underlined statement is actually equal to this. K times k plus 1 over 2. So now in our next line, we are going to substitute this underlined statement by this right-hand side that we assumed it is equal to. So we're going to have k times k plus 1 over 2 plus k plus 1. Right? I hope that makes sense. So we are assuming that the statement is true in step 3 so that we can use that statement in step 4. And remember, we are now trying to get this expression to be equal to that expression. Right, now what do we have here? We have a sum of a fraction and some just non-fractional terms. All right, k plus 1. What I'm going to do is I am going to put k plus 1 in brackets just so that I can treat it as one term, because it does kind of represent one term. Hey, that's the last term. Now, what would the LCD be over here? It would be 2. So if I wanted to write this over 2, I would have to do this. I would have to say k times k plus 1 over 2 plus 2 k plus 1 over 2, right? I'm writing them both over the LCD so that I can now add them together. So if we write this all as one fraction, we're going to have k times k plus 1 plus 2 times k plus 1 over 2. Now I'm running out of space, but do we see that we have a common bracket? So we're going to take that out. We're going to say k plus 1 times k plus 2 over 2. Right? And that was actually equal to the right-hand side. Now, I did forget to do something. I did this right-hand side calculation on the right at the top, but I actually was supposed to write it here, okay, so that you know like what you're supposed to be working towards. So let's just, hopefully you have space, let's just add it there in the first line where we say 4n equals k plus 1. The left-hand side would be this, and the right-hand side would be this, and then we try and make them equal. So I'm just going to add it here. So my apologies for not writing that from the start. I just wrote it in the wrong place. Okay. So now after that, there is a long thing that you need to write down. You actually have to write kind of like a little paragraph that you're going to have to write down every time that you use mathematical induction. Okay, so I'm just going to turn the page so that we can do that. Oh, excuse the little background there. So now we're going to say, therefore, if true for n equals k, then true for n equals k plus 1. Right? That is what we proved now in that last line. We showed that if we assume that the statement is true if n is k, then we can use that to prove that the statement is true for n equals k plus 1. Since true for n equals 1, then true for n equals 2, n equals 3, and so on. Therefore, true for all n element of natural numbers. All right. And that is it, guys. That is how you prove something by mathematical induction. I think I'm going to stop this first video here so that you can go back to actually going through the example if you feel like you need to. I think you might need to, because it is a weird way of proving something. It is a new concept. Maybe look over example 1 again, make sure that you've written it down properly, and then the next video will be me working through examples 2, 3, and 4. Okay,